Hello, in this video we are going to talk about the last and the most important component of the Swin transformer block called window attention. And also we already talked about the idea of shifted windows, and in this video we are going to talk about a padding technique called cyclic shift when we are using the shifted window idea. Okay, let's start. If we look at our Swin block class, we can see that we just created residual, parent norm, and also feed forward. And now we need to create this window attention. Okay, let's start creating this class. Okay, we are going to create this class, and this is the most important class that we have. We are going to go over that line by line and explain that. And let's look at the inputs and see what are the inputs. For example, we know now what is window size, which is 7. And also we saw that shifted used in our window attention to tell us if this is a window MSA or shifted window MSA. And this relative positional embedding, we will talk about that later. Let's look at this DIM, stands for dimensions, also heads and head dimension. Okay, our dimension equals our hidden dimension, and it's going to be equal to the number of channels. It's going to be 96, 192, 384, and 768. Our heads equals to the number of heads that we have, and it's going to be 3, 6, 12, and 24. And also our head dimension is 32. Okay, let's look at figure 3 again. One of the things that we saw that when we have this hierarchic structure is that, for example, we have the downscaling factor 4, 2, 2, 2 in the first line. Then we said that we have layers, the number of layers 2, 2, 6, 2. So one of the variables we showed in our class is called hidden dimension, and hidden dimension is basically number of channels. For the stage 1 is 96, for stage 2 is 2C or 192, for the third stage is 4C, and for the last stage is 8C, which is 768. The other variable we showed was the number of heads, and number of heads are actually 3, 6, 12, and 24. And if we multiply the number of heads to 32 for all of the stages, we are gonna get actually the number of channels. So we are gonna get 96 for the first stage, 192 for the second stage, and so on. Okay, so now we know the hidden dimension, head dimension, and heads. Okay, let's go back to the code. In code now we see our hidden dimension, we have heads, and we have head dimension. And now we can see the inner dimension is gonna be the equal to the number of channels. For example, for the first stage, that is 96, because that is we have 32 as the head dimension times the number of heads in the first stage, and for the second stage is gonna be 192, and so on. So it's gonna be equal to the number of channels. Okay, now we have our inner dimension, and let's also define our heads. Okay, self.heads equals heads. Also, let's add the scale, and let's look at our formula to see what is this scale. Okay, if you look at the formula 4 in the paper, so the scale that we just defined is this one. Okay, so D is basically head dimension, which is 32, and head dimension is now to the power of negative 0.5, negative because that was in the denominator, and 0.5 because that was the square root. Okay, and let's see what else we need to add here. We need also to add our window size. So our window size is 7. I also add this relative positional embedding. We will go over that later. Let me also initialize this shifted, and as we said, this shifted is gonna tell us if it is a WMSA or SWMSA. Okay. Okay, now if it is shifted, if self.shifted is true, we are going to shift all of the windows at the same time to the right and down and pad them. Okay, let's see how we are doing that. Okay, if you remember when we explained the shifted window, we said that we are going to shift all of the windows at the same time to the right and down to the half of the size of the window, and we did that to create a connection between the tokens in different windows. For example, now there is a connection between the yellow token and green token. When we do this shift, these regions are gonna be empty. So we have to pad them. Let's look at the paper to see how they pad them. Okay, let's look at table 5, and table 5 shows the real speed of different self-attention computation methods and implementations on a V100 GPU. And they show two different types of padding. The first one, they call it naive padding, which is basically, I believe, just adding zeros to the empty locations. And the other one is cyclic. And then they show the speed difference between these two. For example, for the stage 1, we can see the cyclic is faster. Also for stage 2, or stage 3, or stage 4. And we can also see the number of frames per second for different architectures. And we can see that cyclic shift is faster for Swin T here. So we can see that this is faster than naive padding, or for Swin S or Swin B. Okay, now let's look at the details of this cyclic padding. Okay, cyclic padding is like this. After we shifted the windows, we are going to just get this section from top and copy paste in the bottom. We do the exact same thing for the section B. We get this section, whatever is left over from the left, and we put that in the right section. And also we get this leftover from here and just put that here to cover this location. Okay, so this is basically what we are calling as cycle shift. Okay, for example, in second stage, for padding the empty locations, we get this section from top, the green ones, and then just copy paste here. Or we get this blue section from the left, copy paste here, and we just use this yellow section to fill out this empty space here. Okay? Okay, now let's see how can we write it down, this cyclic shift, in our code. So first thing that we are gonna do is to define how many pixels we are gonna shift. So we said that that's gonna be the half of the size of the window. So we just do this. For example, our size of window is 7. So it's gonna be divided by 2 is 3.5. So we just consider the absolute value. So we are gonna shift 3 pixels, all the windows at the same time, to the right and down. Then we are going to define this cycle shift function. And using this cycle shift function, we should be able to shift the windows at the same time. And also we should be able to shift them back to the what it was before shift. Okay, let's create this cycle shift function, and when we are creating, you will see why we are putting negative here. Okay, let's create cycle shift here. Okay, for cycle shift we are going to use this class, and as you can see, we get the displacement as the input, and then we are just gonna use the torch.roll, and we are gonna tell how the tensor is gonna be rolled. So we are going to roll it with respect to dimension 1 and 2. Okay, let's look at a numerical example to get a better understanding of this torch roll. And in this numerical example, we have a matrix 9 by 9 with 81 numbers, and numbers are between 1 to 81. And we are going to have input as x, and also we are going to shift -1 in the first and second dimensions. And also we defined here that dimensions 0 and 1, those are the dimensions that we are going to conduct a roll on. Okay, let's see what happens. Okay, if we look at this matrix, we can see we have this matrix here, that the first line, for example, this 2, 3, 4, all the way to the 9 is that green section that we had in the picture. Now that is moved to the down. So now that one is here. It's gonna be 2, 3, 4, 5 to 9. Okay. And also we had this left section, which was the blue section, so that was 10, 19, 28, 37, 46, that one is also now shifted to the right. We have it here as 10, 19, 28, 37. Also, we have that yellow section, which for this example is just this number 1 here. Now that one is shifted to the right down. So now it's gonna be here. Okay? So this torch.roll does exactly what we need to do. Okay? Also, we saw that the value that we put in these shifts are going to be negative when we are going to shift the windows down and right. And when we want to move them back to the original shape, so in that case, if we want to move back, so we just need to put the positive values here. And that's the reason when we use this cycle shift, when we want to shift the windows, our displacement, we put the negative value. For example, window size is 7, our displacement is 3, so we are going to put the -3 here. So that's going to do the cycle shift for us. And if we want to do the cycle shift back and get to the original shape, so in that case, we need to put positive value. So that's the main reason we use the negative in our code.